It's such a pleasure to be here. I will actually start with a confession. This is actually the first time I have ever attended NeurIPS, and actually for any AI conference. But you know, as Trent mentioned, I'm actually a hardcore system researcher, but I come in peace. Actually, I come with a lot of love for the AI community, and actually I come representing the system community to actually make a marriage proposal to the AI community. But let me start with the first principles. Start with a very simple question. What is the fundamental driver to the emergence of artificial intelligence? I know many of you probably have thought about this question and probably have many different answers. The simplest answer that I've heard, which I really like, is from Ray Kurzweil. He made it in 2005 in his book, The Singularity is Near, where he actually made a very simple observation that all it matters is computation per second per dollar. And as a futurist, the way he proves his point is he made a prediction and wait until his prediction proved to be correct. So what happens was, in 2005, based on his projection of the exponential growth of the computing power and how much computing power it takes to reach or surpass brain power of human or the collection of all humans together, he actually made a prediction that in 2023, we're going to surpass the brain power of human. It was probably pretty crazy at that time, but not many people actually believed that. But now we can see that the prediction is quite accurate. And the reason that the prediction is accurate is because I think he captured the essence of artificial intelligence, what it really matters. And the way to turn all the computing power into intelligence is through the evolution of computing systems. And of course, now this is where we look at the last 100+ years. We may not have to go that far. Let's actually instead look at the last 30 years. Many of you probably still remember there was an AI winter starting in the 1990s and lasted probably 10, 20 years, depending how you count. While AI is in the winter, the system community has been actually very busy with emerging scenarios and applications, starting with multimedia. This is where we see the development of GPU for specialized parallel computation. And then it comes the internet, the networking, all the distributed systems that we start building to support World Wide Web, web search, big data, and cloud, where we spent more than a decade trying to scale the systems we have, the distributed systems we have, and make it more and more powerful. And eventually, we have made so much progress, we finally managed to climb all the way to this hidden castle where we can actually wake up the sleeping beauty of AI. And as fairy tale goes, they live happily ever after. So this is why I think it's time for system and AI to get married. But there has been a lot of misconception about what systems really are. Since I represent the system community, I just want to make sure that this message gets through. A lot of people think of systems as GPUs or those cloud systems that are very beefy and can do a lot of computations. Other people think of systems as the act of engineering that produce those computer systems. But for system researchers, system is really a philosophy. This is how we actually manage the increasing complexity and how we actually create order out of otherwise pretty chaotic collection of components and interactions. So in order to manage complexity, there are a lot of system principles or mindset that we have been developing over the years. Well, the simplest ones are listed here as system principles. But there's also a lot of methodology that we develop to create systems that are dependable, that are efficient, that can take on very complex tasks. And so for AI, it's not just the systems that are going to support the AI to do training or inference, but really going forward, it will need more of system thinking to scale the impact of AI. Because we do believe that AI is going to transform the whole society, all industries, and all disciplines. So AI has been advancing very quickly thanks to the scaling law in AI. And this is all beautiful side of scaling. And people are talking about scaling for at least 7 orders of magnitude. That's actually very scary to system people. Because in the last 20 years, we have learned a lot of lessons about scaling. So we have been fully exposed to the dark side of scaling, not the rosy side that all the AI folks have been looking forward to. We know that you can't really scale a system by throwing hardware at the problem forever. And you won't be able to get linear scaling, actually far below linear scaling when you continue to scale the system. And when you scale, all the hidden flaws and all the inefficiencies in the design of your system will actually surface, will actually become worse. And everything fails at scale. And when we try to scale a system, it's not really an incremental step. When we get to the next order of magnitude for our system, we really have to rethink all the assumptions because a lot of trade-offs might have shifted and a lot of design decisions might have to be revisited. And even the abstractions might have to be changed. So it will be a completely new system. It's not like you can easily just reuse the code and expect that it will continue to work well. So visually, the way to think about how we scale in systems is that every time you go to the next order of magnitude in your system, you are essentially developing an almost completely different new system. And the challenge you're going to face is going to be exponentially more difficult than the ones you actually solved at the current scale. And it's like climbing the mountains. You actually have to come down from the previous mountain and then start climbing the new ones that's actually much, much higher. And this is actually why the system community actually needs a lot of help in order to continue this journey and developing new methodology to manage the increasing complexity. And this is where I think we need the princess to actually save the prince. So what we're envisioning is this co-evolution of AI and systems. On the one side, as systems scale, what we observe is that because of the increasing complexity, the system becomes more stochastic. It's no longer deterministic anymore. And this actually gives AI a great opportunity to play an increasingly significant role in helping systems managing all this emerging behavior, all the dynamics that is actually beyond the capability of a lot of methodology we develop in computer systems. So we imagine as we have better and better AI capabilities, we can leverage that to build better systems. And of course, when we have better systems, we can support the continuous growth of AI in two different ways. One is to provide systems that can continue scaling the AI capabilities. And second, to infuse the system thinking into AI. So what is the future that we're envisioning? I think we believe that AI is going to be an affordable and universally accessible utility, just like electricity. And it will be seamlessly embedded into our daily lives and work. And more importantly, it will deliver transformative and trustworthy capabilities. And this is where I think AI and system communities need to work together towards that vision. And there are really three keywords here. One is efficiency. The other is trust. And the third one is infusion. So let's think about the core ambitions that we can take on together around all those three dimensions. So I'll start with efficiency. So we believe that AI will reach new levels of efficiency because we know there are actually huge gaps, several orders of magnitude gaps between the efficiency of the current AI systems and, for example, human brains. And that gap needs to close. And also importantly, instead of always relying on AI capabilities on the cloud, on very powerful GPU clusters, it has to become deployable and be pervasively available. And this can only be done through co-innovations in, for example, model architecture, software, and hardware. And this is an exciting challenge for the system community because actually, traditionally, we have always focusing on the software layer and all the hardware folks will focus on the hardware layer, but cross-layer innovations has always been tremendously challenging. But this is now a necessity for us to drive further progress in the field. So I'll share with you some of the progress that we have made in that direction. And everyone knows that the standard transformer architecture, the weights are using 16-bit floats. And certainly, now we're seeing 8-bit FP8, and even, people are looking at 4 bits and even lower bits. So as researchers, we look at some extreme case to see what's actually possible. And we look at 1-bit LMs. So what if we represent weights using only 1 bit? And actually, the most recent proposal is use a ternary representation. So we have 0, 1, and -1. Surprisingly, so far, all the evidence shows that this is actually not only possible, but actually promising. Because it has a very nice property that this design the BitNet is actually scaling friendly. The larger the scale, the better in terms of performance. And when we get to 3 billion parameter models, the gap between full precision LMs and BitNet already being closed, well, based on the perplexity. And we also look at different benchmarks, with the caveats of all the AI benchmarks. But at least it's competitive against the best full precision LMs at the same scale. Why this is actually significant? Because if you look at how the computation works at a very high level, once you actually change this to a ternary representation, you no longer need to do this multiplication then addition calculation. What you need to do is only additions. And the potential is actually pretty huge because you look at the power consumption or the area that you need. If you don't have to support a multiplication plus addition, then there are potentially huge savings. But unfortunately, if you just have this innovation in model architecture and you run on the current stack, software and hardware, you actually won't be able to see a lot of benefits. It's probably actually even zero benefits when you just run on the current stack. So you really need innovations in the system stack in order to support the exploration of new ideas in AI. So this is where our system researchers come in and look at the problem and say, well, for low-bit computation, we have always have this trick of using lookup tables, right? Why do we want to do computation if we can build a relatively small table and do lookups? And interestingly, even in the current hardware, like CPUs, there is actually instructions to support lookups. So we don't have actually to change the hardware yet in order to get the benefit. And it turns out that when we use lookup table, and there's system innovations and engineering involved in order to create this new software design for BitNet, then we can get a significant boost in terms of tokens per second. And if you look at some of the details, so this is one of the experiments that the team has done. And this is, again, this is not in theory. This is actually where we really run on Apple M2 Ultra using the CPU they have to compare, if you use a full precision LM on CPU compared to use BitNet and use the lookup table implementation we have. And you can see that the saving could be quite significant. Again, this is not in theory anymore. And we can even now imagine running inference of 100 billion parameter model on an edge device. And that's just the beginning. Now, we just talk about changing the software layer in order to show that the full benefits of a different model architecture, the different design, in BitNet. But we can certainly go further. So if we know that we're only going to support lookup tables, we can build a lookup table specific tensor core. And because it's much simpler, so for the same area, we can actually pack much more T-flops. And we're talking about 10 times, 20 times of savings per area. And we can go even further to think about leveraging new technology, because now it's not the computation that's the bottleneck. It's always the memory bandwidth. So it really requires a very different way of thinking about the hardware design. The trade-off will be completely different. And for example, we can even look at optics or processing memory, where the memory bandwidth will be further optimized. So there's potential a design of XPU that is specialized to support lookup tables that will give you hopefully another order of magnitude improvement in all the major dimensions. And this is just one of the sort of research projects that involve both AI researchers and system researchers. And in Microsoft Research Asia, in the last 2 years, we start to see that the AI researchers continue to benefit from the participation of system researchers when they design new model architectures. Every innovation they do, there's always a couple of system researchers trying to give the feedback on what makes sense to make sure that whatever new model architecture can run efficiently. But this is still done manually, so there's a lot of space for improvement. And over time, we also start to see that the system researchers benefiting from innovations in AI. And 2 of the papers listed here are going to be presented in this conference. But as I mentioned, currently what's happening is that a lot of interactions are done manually. If we really want to push the envelope further, one of the problems that we have to solve is, now if we come up with a new model architecture, it has to run efficiently on the current hardware, which is GPU. And if it doesn't, there's no chance for the model architecture to survive. And similarly, if you come up with a new hardware, then you have to make sure that existing models will run efficiently on this new hardware, although all the existing models have been really designed and optimized for GPUs. So we really need to think about new abstractions and new intermediate representations that can decouple the two, so that innovations in model architecture and innovations in hardware can actually go more freely. And it's possible, and we hope to see this co-innovation in model architecture and hardware, where you have much better hardware and much better model architecture that fit together very nicely. I think, given the stronghold of GPUs, we probably need 100 times or 1,000 times the performance improvement in order for this new combination to be feasible. And we're hopeful that this will happen when system researchers and AI researchers work more closely together. So the second topic that's also very important is trust. And if you think about trust in systems, we always try to make sure that the systems you use is reliable. Everybody expects the systems to deliver what's expected. So trust has always been a core consideration in the system community. And with AI, the situation is certainly more complicated, but also more promising. So you think about the interaction between systems and AI. One advantage of systems is we always provide systems provide immediate, direct, accurate, and truthful feedback. So you just run whatever, and then the system will give you an answer. And the answer is the answer that can be repeatable and so on. And that's actually a very powerful paradigm. If you compare with a lot of other domains that AI try to make a difference on, for example, sometimes you need human feedback. Sometimes you really have to wait for some simulation to give you a result, and it's not even accurate. And maybe you also need to do the modeling of the physical world, or you have to wait for some biological or chemical process outside of the system to actually complete. And so how can we leverage this property? But let me actually start with a very simple primer on how system community thinks about trust. The way to think about this in systems is, we're always trying to create a very small trusted computing base so that, we have a lot of confidence this is actually correct. And one methodology that the system community has been developing is to create also the programming language community as well, is to create this verifier, because it's actually very hard to make sure that everything you do to build a system is correct. But instead, we only care about the result. So what we do is, if you have a system, you just ask the verifier to check whether certain properties that you really desire are actually true. And so there's this principle in systems to say that, I can trust you, but I want to verify. And in many cases, the verification is actually cheap. So you can do, if you want to create a solution or create a program, it takes a lot of effort. But checking whether that program satisfies certain properties is relatively cheaper. And so now we can use the same paradigm in the interaction with AI. So it used to be that the reason that we need all this mechanism is because we have to guard against buggy software or even attacks, malicious attacks. But of course, AI also hallucinates, and sometimes doesn't necessarily give you the right answer. But it's good. It's very creative and it's stochastic by nature. But how you can interface with a deterministic system and provide the kind of guarantees that the users desire. So one thing you can do is you send a lot of proposals and you go through this verifier, something that you trust outside of the AI part of the world. And sometimes you give feedback saying, oh, something's wrong, it doesn't pass verification. Hopefully the feedback will be useful for AI to improve its ability to create something correct. Or sometimes, if they get it right, you get a certificate saying, great, this is something that I can accept. And again, that's a useful feedback for the AI system. And looking at what AI is capable of doing today, we're actually very excited about the potential of AI transforming how we do verified systems. So verified systems is a field that has got a lot of attention in recent years in the system community. I think in the last 10 years, at least one session in the top system conference like SLSP or CI will be dedicating to verification. Because there has been a lot of progress in formal methods, formal verification, and the combination of systems. The holy grail for the system community is always to say, would it be great if we say, this is a mission-critical system, and rather than try to test it and show that there are no bugs, we can actually formally verify that this system is actually correct with respect to the assumptions, the specification. And it has been a relatively small community who is capable of doing integrating formal verification with systems. But yet, a lot of progress has been made. So I'll give you one example. This is work from MSR Redmond. It's actually very fresh. This is the latest published 2 months ago actually last month in SSP in Austin. And so on the left, this is just Rust code. And now, if we want to make sure that we can prove that the Rust code is correct with respect to some specification, what those researchers propose is to add annotations. And those annotations are logic-based. So you can see the green one actually shows the precondition and the postconditions of this program. And the red one is an invariant that you need in order for you to construct a proof. And now if you have a formal specification and some of the invariants or other pieces that you need as a part of proof, what they do is they actually created a verifier called Varus. This whole language, this extended language is called Varus. And then you can actually throw this to a verifier. And the verifier will say, wow, this piece of code is correct. What's beautiful about this approach is it just looks like it's an extension of, it's a language, right? You just write a piece of code. It's just, they snuck in some formal verification components. And that makes us wonder whether, we know AI can generate code, but can we actually leverage AI to generate provably correct code? And that would be, for system community, that would be a dream come true. Finally, we can solve this challenge of verified systems. And hopefully, all the systems that we have will be more trustworthy as a result. So we tried. The initial experiment wasn't very encouraging. And this is actually pretty hard task to take on because the number of people who can actually create those various code is actually very small. And we don't have a large corpus of code lying around. So we actually have to manually create 150 those tasks as our benchmark. And then we also created some other code base for training and other purposes. And if you just use GPT-4o, it doesn't know. It knows how to generate the Rust code to some extent, but it doesn't know how to generate all this formal verification pieces. It knows a little bit because there's other language that has those precondition posting looks like it. And even with a lot of prompting, we actually have people looking at adding those methods that we use to create those invariants or those specifications. And we have this 720 hours. So you think about how long that is. It's about the time of one summer internship. And then you don't why. And even with all the work, we create, training examples about 3,000 and so on, but still doesn't have a good enough coverage. So we still get to 30%. And it's a small benchmark, remember. 30% doesn't mean much. But it's a great starting point. I think this is going to be the same pattern for AI to work on hard problems where you don't have a lot of existing data to leverage. You have to follow the same journey that we actually went through. And so now we want to teach AI to generate proofs. Remember, the system can provide, we have verifier, we can actually provide feedback. And so the LLMs are very good at creating all kinds of variations, and some of them might be correct, some of them might not be. But if it's correct, then you get positive feedback. And then you can fine-tune your model, hopefully integrate that success into the understanding of AI about formal verification. And also, there are error cases, right? And we certainly want to leverage the error cases as well. And they're actually more abundant because most of the cases, the LM actually fails to generate something that's correct. So you have to try many, many times. And every time you fail, you get some feedback, and that becomes part of the data set that we can use to help AI understand how to write formal statements. And certainly, at some point, the error is fixed, and we get that as well because, we have the feedback loop. So this is sort of the self-debugging case. And also, not only LLMs understand how it works, but also it understands how to fix some of the problems. And once we have that, then it becomes pretty interesting that we can increase the success ratio much higher. And of course, as I started looking into AI, I realized that the benchmarks in AI don't necessarily mean anything. And unlike systems, when it give you numbers, it's actually reliable. But so it doesn't mean that we have solved that problem. In fact, we're probably pretty far away from solving that problem because the data set, we only have 150 handcrafted ones. So one of the grand challenges is to see whether we can enable AI to think and reason with the rigor of formal methods. And we're also curious whether AI with training in formal methods will be able to improve its reasoning capability in general. So finally, I want to talk a little bit about how we can actually develop a new system, like AI-infused systems. And the way we think about this is AI is actually very good at analyzing data, identifying patterns, and creates new, better proposals. But for systems, they're very grounded. We can validate whatever proposal from AI, and we can actually compile this into code that actually executes, and we'll get the feedback back to AI to analyze the data. So we want to enable this feedback loop. Let me give you two examples very quickly. One is, the best way to think about this is if we want to improve the system, it's better be the system that will also help AI. So AI helps systems and in turn will benefit. So we look at the AI infrastructure, and one of the key pieces is collective communication. And it turns out, for distributed model training or inference, 30 to 70% of the time is spent on collective communication. And it's not like you solve collective communication, provide those primitives will be done. There are many different options and algorithms you can use. And it turns out that different algorithms will work better for different settings, depending on hardware or workload you have. And the difference could be very significant. It could be 3 times more efficient if you use a special algorithm. So we have to design an algorithm for a particular scenario, for a particular hardware. And we do that manually. And it takes 2 days for an expert. The question is, can we do better? But if you look at how this is done, so we have this nickel implementation on top of nickel. Basically, we talk about how we schedule those communications and how we come up with the implementation. What we could do is we can actually give AI a specific problem, saying, why don't you come up with a schedule that works and try to produce the best metrics. And we actually also send all the system feedback to AI so that they can develop the best schedule. But once you have the proposal, which is a new abstraction that we create, then the system side can actually do the validation and do the compilation and generate the code. Because this is what very deterministic part. We don't need the AI to work on it. We actually try to ask AI to generate some code on the left. Doesn't really work very well. So what's powerful here is we want to separate the concerns and give AI the task that AI is very good at. And the result is actually very, very good. I mean, we have solutions that are high quality, and now we have AI doing the work that's much faster for the repetitive thing that experts have to do in the past. And this is actually in production, so it's not a toy example we're talking about. And the reason that AI can do so well, and we actually look at this system, which is called Optiflow, and it actually develops quality system intuitions, which is very encouraging. If you analyze this particular example, then we'll say, oh, we need to avoid cross-socket contention. And then it come up with a better proposal. And this is one of the examples where it does actually better than the experts. And it detects that by analyzing all the data and getting that intuition, which is very powerful. And similarly, there's another example of congestion control, just to show that this paradigm is actually general. And again, we want to come up with rules that help us deal with congestion control, and we send all the system performance back to AI so that it can come up with new rules or better rules. And then we use the system to do validation and code gen. And this is the example where actually it's used in WebRTC for video conferencing, for example, where again, we have to design different congestion control algorithms for different scenarios. And now we can use AI to help address this challenge. And again, it does this much more efficiently than human experts, and the results are much better. But what I'm trying to get at is there is this grand challenge where there's going to be a new paradigm in systems with AI. And we need to figure out what that paradigm is so that we can harness all the power of AI in being creative and can address very hard problems, but also the stability and the trustworthiness of the system, the deterministic nature of the systems. And it's also interesting that to ask whether AI can eventually develop all those system intuitions and come up with those new paradigms, and also generate the code for those compilers on the system side. Just to conclude, we believe that AI and systems together will actually unlock the next frontiers. We talk about the ambitions around efficiency, trust, and infusion. We have shown some of the progress we made. We have also listed some of the grand challenges that we have to address for those to be solved so that we can achieve our vision together. And I want to thank a lot of our colleagues who actually contributed, and also the work has been done by many of my colleagues at Microsoft Research Asia in the Asia-Pacific region. Thank you.
Thank you so much. This is such an inspiring talk. So I'll ask the question get highest vote on the slide. So the first question is, how do you balance the trade-off between flexibility for novel model architectures vs building faster, more efficient, like tightly integrated hardware linkage, model hardware linkage?
Yeah, I guess the question is how you balance the stability of model architecture?
Flexibility.
Flexibility.
Of the novel model.
Yeah, so I think, there probably need to be a new way to think about how to connect the two. Like some of the, so we want to unlock some of the innovation in model architecture without being constrained by the hardware. And currently, I think the question also shows that there's a lot of dependencies between the two. And I believe there are system innovations that can untangle that unnecessary dependencies. And that will unleash a lot of innovations in both places, like in the model architecture and also in the hardware. But they have to come sort of hand in hand as well.
Yeah, the next question, I think the question was asked during the bitnet type of the part of the presentation. So it says, with the ternary representation, what are the limitations? So if you think about how to support different type of nonlinearity and all these things.
Yeah, that's a great question. I think our AI researchers have been still looking at the problems, and because if you just look at the perplexity, that's probably not enough to show that this is good enough. We actually look at also some of the reasoning tasks and so on, and also look at the scaling laws, how the scaling law works. But so far, I think all the results have been pretty promising. We haven't seen any red flags that shows that there's a clear limitation. But I think we only get to probably 2 billion parameter or 3 billion parameter models. And so there's certainly more work to be done in that space.
Yeah, we'll go for one of the questions from the mic.
Hi, thank you for the talk. I'm Wei from OLEDWave. I have a very general question, which is regarding the life cycle of hardware. It's relatively way longer than the software algorithm. In your opinion, do you have any comments on how the software guys and hardware guys should work together to resolve these? Thank you.
Yeah, thanks, Wei. I mean, that's a great question. I think certainly AI is accelerating, and the pace is much faster than both the software and hardware. And hardware is notoriously known to be the innovation is actually slow because it's very costly to try a new idea. But I see a lot of potentials in using AI to speed up the process, even in hardware design. I think there is actually a workshop at NeurIPS that talk about how AI can empower, chip design and some of the hardware innovations. So I'm actually hopeful that the AI can speed up some of the innovation cycles. And I think also, that if we can do this together cross-stack, that will also speed up sort of the meaningful innovations together.
Thanks.
Thank you.
Good morning. Since, in my understanding, GPUs often spend a lot of time waiting for, say, gradients to be shared across nodes and distributed training, the bottleneck is effectively the interconnect. And you talked about primitives for kind of at the software level.
Right.
But to what extent do you think interconnect improvements in terms of latency and bandwidth are more important than chip innovations? And what is Microsoft doing to that end?
Yeah, that's a great question. I think interconnect is essential. And you see a lot of innovations in the industry around interconnect. And I mean, even in Microsoft Research, I think there's actually work in MSR Cambridge that talks about how we can innovate interconnect using optics. And this is quite orthogonal to some of the examples that I'm using, but that's sort of one of the dimensions of innovations that we need. But again, when you have new interconnect, then the whole stack have to go with that new design and figure out where the trade-offs lie. And I think this is aligned with the point that I was making. But there are many possible innovations from all over the places, and interconnect is one of the major ones that we should pay attention to.
Thank you.
Yes, here. Yeah, I have a very quick question here. So there has been a recent controversy, I think published in Nature paper about Google's work versus Synoptic's comments. I just want to hear, because that issue relates to AI helping system, right? I would like to hear your opinion about that controversy.
Yeah, actually, I don't have a lot of context for this controversy, but my understanding is any innovation you do, you have to do it scientifically. And of course, when you are leading some of the innovations, there might be controversy, there might be questions. And I think we just need to address those scientifically.
So yes, very, very nice talk. Thank you very much. I've got a question about trusted infusion and whether it's possible, or actually whether you're already looking at trusted infusion just for software AI co-design and in terms of trusted infusion. There's lots of areas where software systems could potentially be improved. For example,
right.
error messages. If you've ever used a recent C++ compiler, for example,
Right.
and you can have a very small error, but it generates several pages of errors, and AI systems could summarize. And I could imagine for networks, software systems, and many other software systems, AI could significantly improve things like feedback. And what you learn in terms of trust and infusion from software AI co-design could potentially be applied to hardware, except it's less costly to build new software than it is to build new hardware.
That's an excellent observation. It's actually true. The reason I use formal verification is I want to push the difficulty level to the extreme, but there are actually a lot of low-hanging fruits, and a lot of things we can leverage the same paradigm that I described. And I think they're much more achievable and much more practically useful than sort of the holy grail of getting to verified systems. And I think we should definitely start there.
There's more questions online. There's actually a lot more questions online. I'll start with the first one that's relating to one of the previous questions. They say, with this promising results of this quantization, and then there's another work stream on system that is analog compute. So which part will win? Does it indicate that analog is not really promising anymore?
Yeah, that's another very interesting question. I think I'm using BitNet as one example, one exploration, and there are researchers working on other options. Analog is certainly one, and actually, if you think about how human brain works, analog certainly holds promises. But before we can make analog work, there's a lot of pieces of innovation that's needed, and I think it falls to the same paradigm that I was talking about. We really need to think about how the whole ecosystem can evolve with all the new ideas so that we can explore, for example, ideas in analog systems much faster than we currently do. Because now, if you want to try analog system, I don't know how you can get started or how you can make a convincing argument that this is promising. So I think the point I'm making is that we try to lower the bar with this mutual understanding between the system community and the AI community to see what actually matters in those explorations. And then we can move those explorations much faster, can accelerate the progress.
Hi, thank you very much for your talk. It's very interesting. So in the machine learning community, there's this thesis which is called the bitter lesson. I'm not sure if you're familiar with it. So I just wanted to understand how some of your comments seem to be suggesting that or your slides rather, are kind of suggesting that we should be using some of these specific rules when maybe that is not the history that we found to be useful over the last 50 years.
That's a good question. I mean, I think scaling certainly is very important for AI, and we still see the benefits of scaling. And maybe there are new dimensions of scaling that we're seeing. The point I'm making here is this is really about how we can increase the capability of AI in general, right? And reasoning and all the other capabilities. But when you use AI in a real setting, there are many other problems that you have to solve. And that's the part that I think system thinking is going to be tremendously helpful. And this is where we need a new methodology and so on, really to make sure that all the power that AI has can actually be used to solve some of the challenging problems we have in a very trustworthy way. So I think this is not conflicting. So your observation still stands.
Okay, thank you. Could I ask just one follow-up question?
Sure.
Maybe not a follow-up question, but in one of your slides related to the Kurzweil sort of curve, it showed sort of this increasing trend that's going to continue through maybe 2045. So in my experience, it's always good to have a model of the future and sort of work towards that. So, what are the underlying trends in that curve that are going to be at, say, 2035, which you think are mostly going to affect the systems community or the AI community?
Yeah, I think going forward, I think this curve is probably going to continue, and it's going to affect both systems and AI community. And there will be new challenges for system community, but also it gives AI the first further progress in AI a chance to really reach the next level. But also feel like there are other dimensions that we should consider at the same time. And it would be interesting to actually think about what the other deciding factors and how that evolves in the next 20, 30, or 100 years.
Thank you.
I think we're at time now. Let's thank the speaker again.
Thank you.